Hey everyone, welcome back to Robotics. I hope you guys are doing well. Today we have our 15th lecture on inverse kinematics. So to get us started, I've got a video. Now this is a video of robot-assisted feeding. The idea is that for users who might be suffering from a long-term physical disability, we can maybe develop a robot that helps them eat on their own. The user will tell the robot what it should pick up, in this case a strawberry. The robot will then stab that food item and carefully bring it to the user's mouth. I want to make sure I'm very cautious when I transfer the food from the robot to the person so we don't cause any injuries. Now, one really fundamental concept here is understanding how I need to configure my robot arm in order to pick up that strawberry. Like maybe I know exactly where that strawberry is in space. I know its exact XYZ position, but I need to figure out what joint values do I need in order for my robot to pick up or acquire that strawberry. And that concept is going to be really key in today's lecture. First, I'll explain what are inverse kinematics. And second, I'll explain how you can find the inverse kinematics for some pretty simple robot arms. All right, so before we start talking about inverse kinematics, let's flash back to what we already know about forward kinematics. So forward kinematics is a mapping from my measured joint position to the position and the orientation of the robot's end effector. It's specifically this transformation matrix that takes in theta, the position of each of the different joints, and then tells me where the robot's end effector is. All right, but what if I want to start thinking about the opposite problem? What if I know a position and orientation I want my robot's end effector to have? Going back to that strawberry example, maybe I know exactly where I want to stab that strawberry, but how do I find the right joint values that are going to give me that end effector pose? So if I know the position and orientation of the robot's end effector, what is the joint position theta? And that's what I'm looking for right here. So that's going to be the inverse kinematics. Inverse kinematics is a mapping from the transformation matrix back to the joint values. And you'll notice that this is the opposite of forward kinematics. In forward kinematics, I'm given theta and I'm trying to find t. And here I'm given t and I'm trying to figure out what theta could be to get that transformation matrix. Okay. So now that we have a rough understanding of what are inverse kinematics, I want to figure out how I can find these inverse kinematics for some pretty simple robot arms. Okay, so I've got a little robot over here, and I've got two drawings of the same robot. So let's start off with this left drawing. Here's my ground, and I've got my spatial frame attached right here. I've got a link of length L1 going up to this revolute joint that's rotating around the z-axis. All right, then I've got another link L2 going up, L3 to the right, and then I've got this prismatic joint that's pointing down back towards the ground. And that's where my end effector is for this robot. And I'm saying its XYZ position maybe is known, or I have some sort of target XYZ position I want to reach. So this is a side view of the robot. And then here's a top view of that same robot. So we're looking down at the robot. Here's this revolute joint right here, is right here. Here's the prismatic joint from above right here. And then here you can kind of see how this whole thing rotates as I turn that revolute joint. So if I want to reach some very specific XYZ position, for example, I want to stab that strawberry, and let's see, it's right over here, and I know where the strawberry is. So if I give you a target XYZ position, you need to figure out what values of theta 1 and theta 2 are going to be able to reach that XYZ position. And that's a problem in inverse kinematics. Maybe you want to take a second, pause the video, and see if you can solve the inverse kinematics problem for this simple robot arm. All right, let's start by just going joint by joint. And I think the easier one is probably thinking in terms of theta 2. Even though it's the second one in the chain, I think it's the easier one to think about. So this one's going to govern the height of my robot's end effector, right? As I actuate this prismatic joint, I'll be moving up and down. And so if I say I want to reach this specific height z, I can probably use that value of z in order to figure out the correct value for theta 2. And what I can do here is I can just add up my different link lengths. I know that the default height is going to be L1 plus L2. And then if I start actuating this, it's going to move down theta 2 units. So the height z is going to be L1 plus L2 minus theta 2. I just take that equation and then solve it for theta 2. And that's going to give me my inverse kinematics for this specific joint. So theta 2 is going to be equal to what you see right here, L1 plus L2 minus z. So now if I give you a value of z, you can tell me what value of theta 2 you need in order to reach that value of z. Again, that's the concept of inverse kinematics. All right, but that's only half the battle, right? Because I've got another joint I need to worry about. So let's look over to my top-down view, and here I'm going to think about that first joint. So if I give you an XY position, can you figure out what value of theta 1 I should have? Again, maybe you want to take a second and think about it. Now, most of you probably guessed something along the lines of sine, cosine, and tangent, and those are good ideas. Again, you can use your trigonometry here, thinking about these different lengths and realizing that, okay, my hypotenuse is going to be length L3, and I can project that back down and find the sides of my triangle. Very true. The issue here is that whether you use sine, cosine, or tangent, they each have a limited range. Like the inverse of sine is only defined between negative pi over 2 and pi over 2. And similarly, the inverse cosine will only give you values between 0 and pi. So if you've rotated more than that range, you won't actually get back the right answer. And so that's why in robotics, we like to use something called the a tan 2 function, what you see right here. Now, this is going to give you a correct angle anywhere between 0 and 360 degrees, or between pi and negative 2 pi radians. And it's defined like what you see right here in this equation. Now notice that it's y comma x, right? So when you're using it, when you're implementing it in MATLAB or your other programming language, make sure you get the right order. It's usually y comma x, which is opposite of what we normally think about. So one side of this triangle, that's going to be my x position. The other side of the triangle, that's going to be my y position. So I've got x units over, y units up. The hypotenuse is length L3, so I can just use y comma x right here, and that'll give me this angle theta 1 anywhere between 0 and 360 degrees, or negative pi and pi. So it'll give me a value for that no matter where I am for this joint. Okay, so if I put those two concepts together, I've now got the inverse kinematics for this robot. I recognize I've got, if you give me x and y, I can tell you the position of the first joint, or the position it should be. And if you give me a desired value of z, I can tell you a good value for theta 2. So you give me x, y, and z, and I can now tell you, hey, here's a theta 1 and theta 2 combination that's going to reach that desired position. So for this simple robot, these would be the inverse kinematics. And you'll notice that the process we followed was kind of ad hoc, right? It's very specific to the robot we're looking at and some of the geometry that we exploit for that robot. And for simple robots, that's usually the way we go. You sit down, you look at it, and you think about its geometry, and hopefully you can come up with a set of rules that you can use to find its inverse kinematics. One challenge with inverse kinematics is that they often have more than one solution. And I can give you kind of a drawing right here. So let's say I've got this robot. It's got 3 different revolute joints. It's moving in a plane, and here's its end effector. And I want to reach this specific end effector position and orientation. I want it to be at this 45-degree angle with this specific position. Well, if you think about it, there's 2 totally different ways you can reach that desired position. One is the elbow down configuration, and the other is the elbow up configuration. They both are valid answers. They both give you that same transformation matrix T. They're just 2 different ways of reaching it. And here I've shown both of them in the same drawing. Right? And that's often going to be the case. So here's for a simple robot, and here's the same is true for a more complicated robot. This is the Stanford robot arm. And you can see again, all 4 of these drawings have the exact same end effector position orientation. They're just reaching in that same position orientation in different ways. So with inverse kinematics, there are often multiple solutions. And this is a good thing and a bad thing, right? The challenge could be, I don't know which one to pick. The good thing is we can think about how we pick the best one given our robot's current configuration, or maybe some other objective. We can try to find the best choice for my inverse kinematics. Okay, so in today's lecture, we introduced what are inverse kinematics. And then also we went through a kind of an analytical process for finding the inverse kinematics for a simple robot arm. I'd encourage you to practice these concepts with the practice set. You can find it in either the description or the pinned comment. The first page has got the problems, and then all the following pages have the solutions to those questions. Once you've gone through that, we can move on to the next lecture. And this will be kind of trying to expand our understanding of inverse kinematics. So the analytical method I showed you is going to work for very simple robots, but we need something that will scale up to more complex robot manipulators. And that's what we'll start talking about in the next lecture. So I look forward to seeing you there.